Before we get started, does anybody have any questions? Okay. And let me grab my note here that I had to myself. Oops, that looks like my grocery list. I must have brought the wrong thing with me. Doesn't matter. Okay, let's take a bit of a problem here. Let's assume that on an exam, we got 06, B8, OA, DC given to us. Somebody tells us this is UTF-16 Little Indian. The question is, what is the code point? And what is the character's name? Now, I realize you could just look it up. But the reason we're learning these things is not so that we can get the exact answer every time. It's so that we can go through the process and use and apply these same processes to things that you might not be able to look up. On an exam, if you were given this question, one of the things you'd be asked to do is show your work. So looking it up becomes quite a bit of a problem because you can't show that, and you'd be missing all the steps that led to the answer. Okay, Mikkel, what is the first thing I need to do? Jay, can you tell me?
Do you convert it into binary?
Well, we could, but there's a step we're probably going to do in. Basu, can you tell me what it is?
We subtract 10,000.
Well, not yet. That's going to happen in the process at some point. Peter, can you tell me?
Okay.
No, put your hands up if you're going to need to be called. I'm calling on Peter specifically right now.
I just needed to tell you my mic wasn't working. That's why I couldn't answer.
Okay. Peter? Yeah, Peter, what's the thing we need to do here? Your microphone is not working. Okay, Samuel, what's the first thing we need to do? I'm assuming if nobody, when you're not answering and I don't see the microphone come up, that you're not sitting in your chair. So to participate, you need to answer the questions. Scott?
First thing I would do, just to make life easier, is rewrite this as UTF-16 Big Endian.
Yes, you would. That's exactly the right answer. I hope everybody heard what he said. And Scott, while I have you, what would be the Big Endian form of this?
D806 DC0A.
That's exactly right. Okay. Next step we're going to do, somebody's mentioned it already, but let's find out. Frank, do you remember what it is?
Wouldn't you separate it into surrogate pairs? So you got your high surrogate and you got your low surrogate.
Well, we've already done that. Priyanka, what would we do? Andrew, what would we do?
You would put it into binary?
Yes, you would. That's a very good answer. Very much. Can you tell me what the binary is for this number?
It would be 1101 1000 0000 0110 1101 1100 0000 and 1010.
Okay, excellent. To binary. This is not necessarily the next step, but it's one of the next two steps. We can put it into binary first and then subtract away the high surrogate and the low surrogate. Or would probably be easier on us before we do the binary. We're going to keep it as binary there. But before we do that, let's subtract away the two surrogate base numbers. So if we do that, we're going to get 0006 000A, which means that these first two bytes here really would just be 4 zeros. Probably easier to do it that way. Okay, now, once we have our 16 bytes, what would be the next step we need to do? Mikhail?
Is it you separate the two binary things you got into 6 and 10? So like
Right, we're going to need to get rid of the 16 bits and reduce them down to only 10 bits. So for this guy, he's going to be those bits, bring it down here, it'll be the rightmost 10 bits. This guy will be the rightmost 10 bits. We take this number, I'll write it again. We regroup it in sets of 4. What we'll find is this number. Okay, what's the next reasonable thing to do? Who wants to try to give me that? And Mohammed, you want to tell me?
You convert these into letters, whatever they are in hex forms.
Yeah, we could turn this into hex. We don't have to at this point, but it's an okay thing. What are my hex values for this then, Mohammed?
So 0, 1, 8, 0, A.
Okay. Problem's not quite done. We still have one more step.
Are you waiting for my answer?
Patricia? No, let me have Patricia tell me this one.
You get the opposite of zero. You subtract again the high circuit and the low circuit.
Well, remember, we're working from the encoding back to the original code point.
Oh, you add.
We have to add back in what number?
D80. I'm sorry. D808.
No, we don't want to turn it into a surrogate. We want to take. We started as a surrogate. Mohammed, what do you think?
You add 1,000.
Well, not 1,000.
It's just 1 in the start.
We add a 1 plus 4 zeros. We add that number in, we get 1180A. So we've answered the first part of the question. What is the code point? Second part, what's this character's name? Look it up. As soon as you have the answer, just put your hand up. Okay, so I'm going to take this number. Go here. Go to the Unicode site. Plug it in. And on this page, I'm going to find that number. Since it's in here twice, one will be the character itself, the second will be... Okay, so it's right here. Zoom in. It's the Dogra letter Ka. It's actually Dogra. Dogra letter Ka or Ka. Looks a little bit like our lowercase scripted a. So we were able to answer both parts of this by taking and working our problem through. Anybody have any questions about the steps we performed here? Okay, let's try another one. In UTF, big endian, same two questions. What's the code point? What's the character name if there is a character at that location? Why don't you try to work that following the steps we did up here? Okay, we don't need to do this step from here to here because we're already in big endian. We have this number. We need to subtract from it those two numbers. So this is going to be subtracting away D800, subtract away D Charlie 00. We want our answer in hexadecimal here. Dante, what's the answer? What are we going to get after we do the subtraction?
Sorry, I'm still working on it. I'm a bit slow at hexarithmetic.
Stephen?
I'm also still working on it. Do you hear? But you went in hex, you said?
Yeah, just use hex.
Okay. 1 second. I'm still working on it.
Well, if we were to look at these two numbers,
Oh wait, you just want that?
what's 2 minus 0? It's a 2. What's
Oh,
1
okay.
minus 0? It's a 1. What's 10 minus 8? It's a 2. What's d minus d? It's a 0. Okay, what about this guy? 4 minus 0 is a 4. 3 minus 0 is a 3. 13 minus 12 is a 1. D minus d is a 0. Now we have our two numbers. Need to write those out in binary. Go ahead and write those out if you're still working on it. Robert, what should it be?
I have 0, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 1, 0, and 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 1, and 0, 1, 0, 0.
Okay, that sounds right. Now, what did we do to these two numbers procedurally? Who wants to tell me that? Raise your hand if you know. Nimmer?
We cut it down to 10 bytes on each side.
10 bits, not bytes. 10 bits.
Sorry, 10 bits.
Sure.
For the step where you subtract the surrogate and the lower surrogate, do we always assume that the left side is going to be subtracted with the higher surrogate and the right one is going to be subtracted with the lower surrogate?
Yes.
Okay. All right. Thank you.
Always. Okay, so we get rid of the first 6 digits. Let's copy this line. Get rid of the first 6 digits. Second half, get rid of the first 6 digits. Now we take this number, combine them, and then put them into groups of 4. You can write that number out in hex. Who wants to tell me what that number is in hexadecimal? Patricia?
That's 8, 4, 9, 3, 8. Oh, sorry. 4.
Okay. Are we done?
No. You need to
What do we have to do?
add what looks to be 10,000.
Yeah, we have to add that to it. What's the final answer going to be then, Robert?
94934.
Okay, that's the code point. Let's look it up and see if that code point exists. Nope. It's legal, but there are no characters currently defined in that range, which is okay. So that's fine. If you were going to do that, this is the answer you'd put down right here. I think you're making this too hard for yourself. And that's one of the things we want to do is we want to simplify all of these processes. That's why computing a surrogate is not nearly as important as being able to see what the steps are and then follow the steps, which of course go back to the basic principles. You have to know your binary, you have to know your hex, you have to be able to think through an algorithm. You have to be able to then go ahead and process the details. Okay, let's take and do one more thing here. Let's assume for a second we were given the, I don't need this anymore. We're given the number CEA9. UTF-8. What we want to know is what's the code point and what's the name of the character. So jump in and think about it. Now, we haven't done one in this direction in class, so if you practiced it at home, you're ahead of everybody, but shouldn't be that hard to figure out. We have the UTF-8 character. We want to know what the code point was that generated this UTF-8 character. Just put your hand up if you have an idea what the encoding would be, because that would be the next step, is to try to put this into some reasonable way of reading it. Okay, a reasonable first step is to put the number in binary. So Dante, what's the binary for this?
The binary would be 1100, 1110, 1010, 1001.
Okay. Now, Unicode is always bytes. So we know those two are put together. Those two are put together. We can always look at the start of the character to figure out how many bytes long it is. 110 means it's a 2-byte character. So these are the first 5 bits. Oops. One zero is the second continuation byte. So those are the 6 bits. So if we break this into, so that's a 4, put a 0 on the front, make it be a set of 4, and turn that into hex. Who wants to give me the hex for that? Mohammed, you want to do that?
Is 3, A, and 9.
Yep. And because we're working with that utility to look the names up, it's going to want a 4 character or 4 hex bit thing, 4 nibble item. So we need to stick a 0 on the front. So let's go look that up. 0389. That's the code point that we would record as our answer, but let's see what the name of the character is. On this page here. Let's see if we can find it here. Here it is, right here. 0, it's an omega. It's the Greek capital letter omega. Now we found 3 of them on the page because we also found what's called the ohm sign. Remember we talked about ohms using the capital letter omega? Well, it's actually a specialized version of the thing, and it might actually look different in some fonts. In this font, they look identical, but you'd have to be sure that you had 0389 as opposed to 2126. Okay, you guys did pretty well with that one. Let's take and do another one here. Let's take something that's going to be a little more fun to do. Let's use hetran. And let's go the other direction. Let's take their number 1, which is this. And let's encode that in UTF-8. This now is a code point. I've been giving you the character and you've been telling me the code point. This is the code point. We want to work the problem opposite what we did here. First thing I think we want to do is determine how many bits are valid in this number. So that's a 1, that's a 0, that's an F, that's a B. So there's 12 bits, there's 13 bits necessary. Now with 13 bits, I can't write it. Well, let me do it the other way around. I can't write it using a leading 0. Won't fit into that either. That's 11 bits. We need 13. So it's going to fit into that number of bits. Since this is 6 plus 6 plus 4, this is 16. We only need 13 of those. There's going to be some leading zeros. The last 6 bits here are this part right here, 1, 1. One zero one one. The next 6 bits are going to be this section right here, 10011. What did I do? Oh, 3 zeros. Now we have 4 bits left. Interesting. Does everybody see what we did wrong? Well, actually, what I did wrong? Jay, what do you think?
You put 9 accidentally.
Well, no, the real problem we have is if you look at this, when we wrote it out, this was a nibble, this was a nibble, 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 F and a B. There's 4, 8, 12, 16, 17 bits. So we have to fit in 17, which means this pattern isn't good enough. What we'll have to do is we'll need the 3-bit version, which means we need 2 more of these in order to get 17. We have to be, I mean, that's still going to give you 16. We need this guy. Because we need to have enough of these 2, 3, 4 to give us 6, 12, 18, 19, 20, 21. This is bigger than 16 because we need to be able to encode 17 bits. So I made a mess of this number. You can easily go back and, Bess, you can turn your microphone off if you're making funny noises. You could go back and undo what I did down here and plug these numbers. Actually, I might be able to recover from it. Let's see. Zero. I remember I typed the wrong character. And then in front of that, we need 6 more characters, which would be What do we have? Oh, we got a space. Okay. And then we had 3 left. Well, it looks like I pulled some numbers down wrong. So I'll tell you what, rather than me making a mess of it again, because we need to move on, why don't you at your leisure, just as a practice problem, take this code point and turn it into UTF-8. You just saw some of the things, and the problems I'm just making a mess of it, so no point in me continuing with that. Okay, other than what's the answer there, are there any questions? In the last case, what you really need to do is make sure after you count the number of bits, you pick one of the pattern items that can hold that many bits. And let's rewrite that little table real quick. You have 7 possible bits. Starts with a 110. You have 11 bits. Starts with a 1110. You have 4 here. So you have 12 and 4, which is 16 bits. You have 17 like we had, you have to go to the next guy, which has 3 here. Which allows the maximum of 21 bits. We only need 17 of them, so there'll be some zeros at the end here. But when you take this number out of binary and stuff it in here from the from the right-hand side toward the left, the answer you get is the answer. Then just turn that back into hexadecimal. Make sure you can reproduce this chart, because for you to do it, 1 byte, 2 bytes, 3 bytes, 4 bytes. And that'll handle all the way up to the 21 bits. So if somebody said you had a 14 bits you had to store, it won't fit in 7, it won't fit in 11, it will fit in 16, so you'd use the 3-bit version. You could fit it into 21, but there's no point because you'd have extra byte for nothing, it'd be all zeros. Okay, anybody need me to go over anything else here? I don't want to work that problem out because I've given you too many clues, and you should actually take a shot at it. And yes, I was making a mess of it. Any other questions about Unicode at this point? Any of the UTF-32s, the big end-ends, the little end-ends, the UTF-8 surrogate pairs? Robert?
So I'm just noticing when I break this down, I get to the end of the 6 digits before I get into the very top one, the 11100.
That's correct.
So that would just be leading zeros then.
Right, and the only reason you know that has happened is because you can't get all the digits in the one that's smaller.
Right.
Yeah,
okay.
But yes, sometimes you will. You'll actually wind up with all this stuff zeros anyway. But it's because they were close to 16 in length. They were just not enough to, they just won't fit in 11. But yes, a good observation. Okay, let's go into another type of encoding that we need to know about. Let me throw this off to the side so I don't start typing from it. What we're going to talk about now is called the IEEE 754 floating point standard. It's a standard for representing numbers with decimal places in them. As we'll see later, normally when you're working with numbers with decimals, you're basically estimating the answer as opposed to getting precise answers because we're working in base 2. Most of the numbers we use for examples tonight will be in base 2 just because it makes it simpler to understand. But you still can encode things like 1/3. It's just they're not going to necessarily be precise, just like in decimal they're not. You know, we can't precisely get 0.3333, any number of them, and come up with something that's satisfactory. We can come up with close enough to do the math, but we can't come up with something that's going to be precise, like adding a binary 4 and a binary 2 together. You know, you won't get that precision. Now, the IEEE stands for the Institute of Electrical and Electronics Engineers. It was originally intended to be kind of a academic, although not a school type of organization, that people who were engineers or worked in the field of electronics, electrical engineers or worked in electronics, could become a member and would have other people, professionals, with which they could write papers, they could work out theories, they could just have friends that were working in the same things they're working in. It's since been abbreviated to the IEEE, and rarely do you hear the full name. I very often don't remember it. But the IEEE and its 754 standard have been adopted by most of the microprocessor and certainly processor world. There are different versions of it. The version we're working with is what's called single precision. And it's a 32-bit notation. And if we were writing in languages like Java, C++, it's what we call a float. I'll put over here, not a double. So it would be the standard that describes how a float is represented by a language like Java or C++ or C# or many other languages. There's other terms for it in other languages, and we won't go through those because this is not a languages class. But you will see these, and it's good to know how to encode them. I very often, because I'm working, with internal memory, looking at the bits that are in the memory, will run across something that immediately jumps out to me and says, oh, look, a floating point number is laying here. Just like Unicode jumps out, particularly surrogate pairs where you see a lot of those D8, D Charlie things in a row. And what we need to do is we need to look at how the floating point standard is encoded, do some examples, and we need to be able to go both directions with it. Ultimately, we'll take a number which is in, kind of fixed point binary and turn it into the floating point standard. There's three main parts to the number we're going to be working with. The first bit is the sign. This is 1 bit in 0 is plus, 1 is negative. So unlike 2's complement, which is the way we use binary to represent a negative number, to represent a negative number in the IEEE 754 standard, we simply set the sign bit to either a 0 or a 1 to indicate in which it should be. The second thing we have is the exponent. The exponent is if you think about a number of some base raised to an exponent. It's the thing you're going to use as the raised to, the power. The is 8 bits in length. And we use an encoding called excess 127, which just quickly means 2 raised to the 0 would actually be written as 2 raised to the 127. So the exponent is 127 bigger than it needs to be. Anybody want to take a shot at why that happens? Why that's a good thing? Robert?
I'm guessing either the first 127 numbers are reserved for something else, or somehow that makes processors.
Okay, well, we could always design the processor to work with any type of exponent. And you're kind of right with the first part of your answer there. What do we normally have to deal with, especially when we're working with powers of 2? Well, things that are negative powers of 2. By automatically raising the base number to 127, we don't have to worry about negative exponents, because 126 would be a -1. 125 would be a -2. And we could go all the way down to 128 if we needed to, because that's the number of bits that are actually reserved for us. But it's going to allow us to represent the exponent as a positive number, even though we may be talking about an exponent which requires a negative component. Inflated by 123. The last part of the number we're working with is called either it's called the characteristic, or sometimes the mantissa, or sometimes the base. We'll probably use all three terms, just depending on what we're talking about. But it's the number you're raising to a power. So these, in fact, are not really 2. They're going to be some arbitrary number that gets raised to that power. These are 23 bits long. So if we're using 32 bits, how many more bits do we have to deal with? Somebody stick your hand up and tell me. Robert?
None.
Right, we've used them all up. 23 plus 8 plus 1 is 32 bits. So we can encode a number by giving it a sign, giving it a number. Let's say we use the number 127. And then we gave it a characteristic. Well, in the case of numbers that meet some certain rules, the number we're going to represent as our mantissa or characteristic is normalized. So in trying to figure out what we're going to encode over on this side, we have to talk a little bit about how you normalize the number. Let's say we had the number that looked like this. And we had a number that looked like this. We had a number that looked like what we're going to do is we're going to shift the number we're interested in. All these are in binary. We're going to shift the decimal point so that in all cases, there is 1 and only a 1 to the left of the decimal point. So this would be 1.01000. This guy would be 1.0. Now, how many places did we have to shift the decimal point here? Well, we shifted it 2 places. Now, if you think about it, if we're going to take this number and raise it to some power, and we get a bigger number when we're done, that means this 2 is a positive number. If, however, in this case, we went 1, 2, 3, we went 4 places, then to get from our big number that we were encoding back to the small number we really have, we'd need to use a negative exponent. Now, why are we doing this? Well, the reason is if we do that, we never have numbers that don't have a 1 to the left of the decimal point, and they never have anything other than a 1. Because of that, we never have to code that 1. We buy back 1 power of 2, which means we can encode twice as many numbers just by giving up that 1 digit. Now, you might say, well, what happens if it's the number 0? What happens if it's, well, we'll get to that later. For now, assume there is a 1 in the number somewhere so we can make that happen. Now, when I say we shifted it by 2, the exponent we're going to really encode is going to be 129. The exponent we're going to encode here, 4 less than 127, is 123. Of course, this guy is already normalized. The number when we're done looks like that. It's still, we're going to shift it 0 positions. So the number we code for an exponent will be 127. Okay, let that sink in for a second. Kind of say what I just said out loud, even if there's people in your house that look at you like you're crazy. Robert, do you have a question or your hand's still up? Okay, so let's take a number and see if we can encode it. Let's first of all just take the simple number we got, 1, which is that top case up there, but we'll write them down here as we go. What am I doing? We're going to encode the number 1. First thing we're going to do is we're going to figure out whether or not the number needs to be shifted in order to normalize it. And it does not. So we're going to shift 0 positions. 0 positions means we're going to compute an exponent of 0 plus 127 or 127, which in binary looks like that. Now, to write the number, we need the sign. The sign is 0. The exponent is 0111, 1111. The number is going to be whatever's to the right of the decimal place, which means we're going to have enough zeros here to get us out to 32 bits. So let's take this number we have right now and crunch it down into, whoops, what did I just do? Crunch it down into sets of 4. Which means we're going to have some more zeros out here. 1, 2, 3, 4, 5, 6, 7, 8. Number for 1 is going to be this. Let's write this out in hexadecimal. 0011 is a 3. 1111 is an F. 1000 is an 8. We need 5 zeros. And that's the encoding for the number 1 in IEEE 754 floating point, single precision. Let's try another one. Let's encode the number 2 in decimal. Encode it. See if you can come up with the procedure you're going to need. Okay. The number 2 written in binary is 10.0. Convert it to look like that. How many places did I move the decimal point?
1.
So what number am I going to encode for my exponent? Raise your hand, somebody. Basu?
$128, sorry.
Okay, so it's 128 will be what we use. 128 looks like that. So now we should know enough to be able to encode this. We have a sign bit of 0. We have our exponent. We know that it's going to be 10, so everything else we code here is going, the number of bits we need is going to be zeros. So let's write that in hex. First of all, let's regroup it in sets of 4. No, there's too many. We got tons of zeros out here. Let's write that in hex. Anybody want to tell me what that is? Raise your hand if you do. Easiest question of the night. Scott?
It'll be 3 0 0 0 0 0 0 0.
Okay, close. Frank?
8000000.
Andrew?
It'll be 4000000.
Yeah, there are 8 of those numbers. So there's a 4 in the first position, and the rest are zeros. It's a 4, 0, 0, and then of course there's lots of zeros out here we didn't code yet. Okay, let's try another one. You guys are getting good at this. If you can do the number 4. So 4 looks like this. And somewhere else, not here. Well, so that looks like 4. We need to make it look like this. How many positions do we shift it? Robert?
2.
Okay, so if we're going to shift it 2 positions, The number gets bigger when we restore it from the 1, so that means it's positive. We have to add a 2 to 127, which is 129. Who wants to give me the binary for 129? Dante?
That's 100000001.
Right. Now, if you were having trouble with that, you can say, well, there's 128. It's one more, so just turn the 1 bit on. You get the same encoding, but thinking-wise, some people have an easier time doing that. Okay, now that we have the exponent, we should be able to encode the number. 0 for a sign, 10000001 for the exponent. The 1 on the left of the decimal is thrown away, and then the rest of it's coded like zeros. You should be able to take this, group it into sets of 4. Now we should be able to write this number out. Matthew, what is it?
0800000.
Okay. Very good. Do one more. Let's do the number 5 as a number. That's the decimal value. Okay, let's work through this guy. First thing we want to do is write it out in binary. That would be a 5. I forgot what number I was working with. We need to shift it. How many positions? We want it to look like 1.010. How many positions am I shifting it?
2.
Again?
2.
2, yeah.
2 positions.
Okay, which means
129.
we still want the same exponent, which is 1. And we can now write our number out. The sign, the exponent, and the number to the right of the decimal point. We group things in sets of 4. Turn that into hex. Who wants to tell me what that is? Put your hand up. Yan Wen?
So the answer is 40800000.
Yep, that's the number 5. What if it were a negative 5? What's going to change? Stephen?
Would that just be negative, or would you just change the binary of that into a negative?
Well, we're going to change the sign there, right here, right?
Yeah, just to 1, which is equal to negative.
Which means this is no longer a 4.
Nope. It's a what? SD? that what it is?
Charlie, yep.
Okay.
So -5 looks like this. Okay, now let's put our thinking caps on. And let's encode the number 1/2. It's in decimal. Take your time, work through in your head what has to happen here. Okay, let's first of all write 1/2 in binary. Using fixed point decimal, it would be 0.1. We need to shift it so it looks like that. So how many positions are we going to shift it? Scott?
-1.
Yeah, -1 position. Okay, so that means the number is not going to be 127. It's going to be what? Here now?
126.
Yeah, so it'll be 126. Now, the easiest way to encode that is not to spend all day doing it, but rather we know, for example, we know this is 128, right? We learned that anytime you take and turn a bit into 0 and make all the ones to the right of it a 1, you get one number less. So we know that if that was 128, that has to be 127. Since 126 is 1 less than that, get rid of the 1 bit. Now we know we've encoded 126. So we said 1/2 was a positive number with 126 as its exponent. Everything to the right of the decimal point gets encoded. Since there's nothing there, these will all be zeros. We can write that now in sets of 4. Let me copy it and do it. So we know at least the first 3 nibbles are 3, F, 0, and then 5 more zeros. So that's the encoding for 1/2. Okay, look at that and see if you could do it. Let me give you one for you to do by yourself. Do 1/4. I can make it negative 1/4. I hope you guys are having as much fun as I am. This is good stuff. Okay, you should be well underway on this. 1/4 is encoded as 0.01. So we need to make it look like 1.0. So how many? Patricia?
2. -2,
Right.
sorry.
It's in a negative direction, yep. So that means we're going to take 127 minus 100, well, minus 2 equals 125, right? Correct?
Yes.
So how can we get 125? Well, we can write out 127, and we can get rid of 2. So there's our exponent. I swear I'm hitting the key there and it just doesn't go. We need a sign. We said it was negative, so we'll stick a 1 in front of it. There is nothing after this, so it's going to again be trailed with zeros. So we'll break this down into nibbles. And we can write those out. Who wants to tell me what this one is? Menotti, why don't you tell me?
Oh wait, I'm sorry. So the first one is B, and the second one is E, and then it's 8, and then 5 zeros.
5 zeros. Yep, very good. Take one that's just mildly more complex than that. It's not hard. But let's do 3/4. So I'm going to be going kind of as we're doing it here. 3/4 would look like 2/4 or 1/2 plus 1 more. There'll be some zeros after that. Shift in order to get the number looking like that. Well, it's actually going to look like that. Scott?
-1.
Okay, so we're going to go -1. Again, we can compute our thing relative to 127 by just getting rid of the 1 bit. Positive number. Here's the exponent. Now we code everything to the right of the decimal point. This time we do have a number. So we code a 1 followed by a bunch of zeros. Break that into sets of 4. And I see a 3, an F, a 4, and a 0. Everybody see that, or did I type something wrong? Okay, good. I got it right this time. Now, there are some special case numbers that we need to know about. First of all, if the exponent is 0 and the mantissa or characteristic or base, whatever we're going to call it, is 0, the number you're dealing with is 0 plus or minus 0. Now, all the hardware in the world compares plus 0 and minus 0 to be equal, but they're encoded totally separately. If I took and wrote out 0, well, I also could write out, and both of those are zeros. Now this requires that other than the sign bit, everything else be a 0. If, however, we've got a dirty 0. Yeah, I know you talk to him online all the time, but a dirty 0 is when the exponent is a 0, meaning it's potentially going to be a 0. But then you look at the mantissa, there's some bits turned on in there. Over in this part of the number, there's some noise. That's called a dirty 0. Now, a dirty 0 is basically what we call, there's other terms used for this, but we're going to use a simple one. Denormalized number. In this case, the leading one we've been hiding is not hidden. And the exponent is always minus 126. So that allows us to have a number looks like that. This one is the one that sits in front of the decimal point, but it's been shifted way over to the right so that you would have blah, 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 1 raised to the minus 126. That is a small number. But we've got them. Zeros are when the exponent and the mantissa are 0, regardless of what the sign bit is. If the exponent is 0 and the other number has some dirtiness in it, it is a real number. It just happens to be very, very small. Now, if the exponent is all ones, meaning it's equal to 255, and the mantissa is all zeros, then we have infinity. Okay, sorry I had a wire fall out. The infinity is plus or minus depending upon which the sign is. Plus and minus infinity are not equal. They're as far away from each other as we can get. That leaves us with one more case. If it's all ones and if the mantissa is not all zeros, we have a thing called not a number, meaning it literally is not numeric. You can't even compare it, even if the bits are the same, against another one just like it, because it's not a number. So any not a number you generate is equal to nothing else and can exist just simply because of the fact you have an exponent of all ones and a mantissa that contains some noise. Now, if we go to our website and go to this last article down here, let me see if I can quickly find. Yeah, this table basically summarizes what we just talked about. They call it subnormal as opposed to a dirty zero, or calling it a denormalized number. But you'll get the idea of what it is. So this article that I added to the end of the thing basically talks about single precision floating point, and specifically in here talks about the IEEE 754 single precision binary floating point format. Well, that's a lot to say. Anybody have any questions about this? Okay, let's do one. Our number is minus 123 and 3/8, which is 0.375. That's 3/8. So let's write it out in binary. Well, a quick way to do 123 is to write 127. Oops. How much less than 127 is 123? 4? Okay, so let's turn off the 4 bit. Now we have the 123. 0.3/8. There's nothing and a half. That would be 4/8. So there's 2/8 and a quarter, 1/8. That's. I'll stick another 0 on the end. So we've now written 123 and 3/8. How far do we have to move the decimal point? Frank?
6 spots.
Okay, let's double check that. I'm sure that's the right number. 1, 2, 3, 4, 5, 6. So let's rewrite this with it moved over there. Or instead of here, we need it here. We said we shifted 6. It's a positive 6 because the number gets bigger when we try to restore it. Okay, so we need 127 plus 6. Okay, now a little trickier. We write out 127. We try to add 6 to it. That's a mess. But isn't 127 plus 6 the same thing as 128 plus 5? We know how to write out 128. It's one more than that number. And then we have to add the 4-bit and the 1-bit. And wham, we've got our number. So this is our exponent. The sign is negative, so we need a 1 in front of it. Now we have to encode everything to the right of the decimal point. That's all of this. Let's break this into sets of 4. We have in here. Now you should be able to convert that into hexadecimal and tell me what the answer is. Try to do that and then give me your hand up when you get it done. See some new clean hands up there in there. I've seen these guys' hands before. Kamulin, what would it be?
I got C2F.
6, did you say?
Yes.
And then what else? What else?
Then 3 zeros.
Yep, you bet. So that's the value for negative 123 and 3/8 right there. Okay, you can practice some of those. Give yourself some challenges, you know. Have your mom and dad, your brother, your sister, whoever is at home. They have the dog. I have Miss Lucy the cat here. She already given me problems to work on. So I think we can say we understand that. Does anybody have any questions right now on this before we move ahead? Robert, do you have a question, or is your hand just still up?
Sorry, I'm real bad at that.
That's okay. We're going to go back into the world of circuits again. So let me clear my notepad here. So let's really quickly go through a diode problem. Okay, so this is LED 1 over here. Put some little arrows coming out of it so you know that it's an LED. This is R1. We'll just call this guy V. He's a 12-volt battery. And we want to know what resistor we need to buy to replace the picture here. And that's all the information we have. We do know the current is flowing that direction, and we'll call it I. Put your hand up if you know what the first design step is. Stephen?
Do you put 20 milliamps in it?
Why would we put 20 milliamps?
Oh, is that's for
That's the right answer. That's the right answer. I'm just asking you why.
Oh, because that's like in the middle between the lowest you could go, which is 15, and the highest which is 25.
Right. We set some restrictions which said this can only be between 15 and 25 milliamps. And you have said this is going to be 20 milliamps. Okay, I'm good with that.
Right.
Second step, put your hand up if you know what that is. Frank, you look like you got there first.
You take the battery voltage and subtract the diode amount, which would be 2.1, and you're left with 9.9.
Okay, so we got 2.1. Here, where'd you get that number from?
In the last lesson, you said all light bulbs are going to be 2.1 volts.
I said unless I tell you otherwise, and I didn't tell you otherwise, so 2.1 is the right value. 12 minus 2.1, what did you come up with?
9.9.
So it's 9.9 volts here, relative to ground. Remember, there's no voltage doesn't move. is a pressure relative to another spot. So this is 0 here. This is 12 volts relative to 0. So the next thing we need to do is to determine the value of this resistor. To do that, we need two things. We need to know what the voltage drop is across the resistor and the current through it. We have the current, we don't have the voltage drop. All right, now, what's the voltage drop?
You divide the 9.9 by the 0.02.
Well, no, we can't do that because the voltage here across the resistor goes from 12 down to 9. What we need to know is what is that distance? What's that voltage difference?
Oh, you just subtract the two numbers.
Okay, so what number is it?
2.1.
Okay, so if it's 2.1 to get to here, and then it's 2.1 to get to here, doesn't there seem like there's something wrong? Scott, what do you think?
Yeah, when we computed the 9.9, that was the total remaining voltage that has to be dropped after we take the LED into account.
Right. This guy here, the point is not 2.1. So be careful about that. That happens a lot. That's why I let it go ahead. But now between here and here, what do we have? Robert?
That's where the 9.9 lives.
Yeah, that's where the 9.9 volts lives. Ohm's law, we're going to say that the resistance we're going to get is equal to the voltage dropped divided by the current through the device. We know the drop to be 9.9. We know the current, and that's in volts. We need this in amps. So in amps, this is 0.020 amps. And that's going to ultimately give us an answer over here in ohms. So we can grab the calculator, because this is a grocery store calculator problem for sure. And we can take our 9.9. We can divide it by 0.02. And we'll get a 495 ohm resistance. Of course, we know we can't buy one of those. So what do we have to do? What would be our next thing? Do we just sit in the corner and cry? Some people do. I had one student one time, he would cry at every single fact he learned. He would say, what a wonderful fact. And then he'd bend his head over and start crying. He was a pain. Okay, Frank, what do you think?
Well, we would have to refer to our standard resistor values and
okay, let's go there. So we need to get our standard resistor value. We don't need that any longer. We don't need that any longer. And what was the value we had?
We came up with 400.
Okay, now, in our use of this, we know in the first place, we're going to take 495, and we're going to only deal with it with two standard digits. So if we, or I'm sorry, significant digits. So let's just turn this into two significant digits right now. What do we have to do? Same guy that was talking, talk again.
Well, in this case, I would round up to 500, but yeah, 50. It would be 50.
Well, we round up. Well, we round up, so it's going to be 5, 0, which are our two significant digits, and one more 0. So it's 500. So what we want to do is look for 500 ohms in our chart. we're probably not going to find it. We're going to get close. What's the closest we can get? Frank, you answer that again.
Well, it really depends. If we're going to go with a 10% deviation or a 5% deviation, it could go one way or the other. So if we want to go with 5%, the 51 would make the most sense. But if we're looking at 10%, that's all they have available, we'd have to drop down to 47.
Right, and the good thing about 47 is it's also available in 5%. So let's use the 510. We call ahead. We know they've got one. So, oops, that's the wrong stuff. So we're going to say 510 is the resistor we're going to buy. But it could be 5% high or it could be 5% low. So we need to figure out what 5% of 510 is. So we can go 510 times 0.05. And that's 26. So 510 plus 26 would be 536. And 510, I can't do this in my head, minus 26 is equal to 484. Now we're going to check these two values for current, and then we're going to pay attention to this guy for power. Smaller resistor means, because of the formula, smaller resistor means that the wattage of these multiplied together is going to be higher because more current will be passing. We need to know here also, this is the maximum current. We have to make sure that doesn't exceed 25 milliamps. And we have to make sure this guy gives us. So let's do those two things. Again, we need the calculator. So 484 is our resistance. We want to compute the current. So we can take the voltage, which is 9.9, divide it by 484. We can come up with two significant digits as 20 milliamps. Okay, let's do the same thing, but with the other value. Of 9.9 divided by 536. That's 18 milliamps. Again, that's right in the... And we'll go back to this guy again. It's 9.9 divided by 484 gives us the current. Well, we can take that current times the 9.9 and get our wattage, which is 200 watts. Actually, it's not 200 watts. It's 200 milliwatts. Now, our choices are 125 milliwatts, 250 milliwatts, 500 milliwatts. This is an 1/8 watt resistor, 1/4 watt resistor. We set our wattage here. This is milliwatts, 200. 200 is plenty below 250 that it'll be safe to use. So we know we need to get a 510 ohm quarter watt resistor. I'm sorry, we said half watt, didn't we? 5% tolerance. What's the color code for this resistor? Look it up, and as soon as you know, put your hand up. I'll be trying to find the page here for us. Hey, Stephen, what is it?
Is it green, brown, brown, gold?
We get green for the 5. Then we have a 1,
Yeah.
which is brown. We have a 0, 1, 0, so that's brown. And then we need the tolerance. Tolerance is 5%. That would be what?
Gold.
Gold.
Yeah.
Okay, yes. And remember that the wattage is not encoded anywhere on the resistor. We have to look at the packaging. But we want to make sure we get a half watt so that if we had picked something smaller than that. Oh, actually, if we could, it's quarter watt. It's not a half watt, it's a quarter watt. It's 250 milliwatts is sufficient for a quarter watt. We had only 200. If we accidentally got one too big, all it does is take up too much space. If we got one too small, it might overheat. So erring on the side of too big is better than erring, but it'd be better to get something that's close and still safe. Anybody have any questions about that exercise? Frank, you have one?
Yeah, I was just curious. When would you opt to go outside of 20? Because you said the safe zone is 15 through 25, and so far we've only done 20.
Right. For your original design, pick one that's right in the middle like that. And then chances are pretty good that you, by making a really good design, because we're only using one resistor here, but if you had lots of them, all of which could be variable, you don't know in advance whether it's most likely to be too high or too low. So to, do the Goldilocks thing here, we can say we want it just right. And so we'll pick something in the middle, hoping that it doesn't error too far either way. So if I told you, for example, that we have a diode and it must be between 20 milliamps and 22 milliamps, the current must be. For designing purposes, would it be better to pick 20, 21, or 22? Anybody can answer that.
21.
Yeah, 21, Stephen, thanks. Because that way, if you erred wrong either way, you've got a buffer zone. If you pick 22 and it accidentally was a little too high, you're out of spec. You pick 20. Now, this would be very hard to meet the spec, but if we got precision resistors, maybe with 1% tolerance, we might be able to meet it. Okay, any other questions about this? That was a good question, by the way. Scott, do you have a question?
Yeah, in the real world, when we're choosing the power rating, if we're kind of bumping up against these fractional ratings here, would you want to bump up? Like if we calculated a wattage of like 245.
Yeah. It's kind of a soft science of figuring out what you need to do there. But if you got a rating that was something like 235, I would start getting antsy about that getting awfully close to 250. If you told me it was 220, I wouldn't be worried. And that's just something you learn over time. I can't give you a really good threshold. But if the number looks iffy, go to the next bigger one. Okay? That's just kind of be the thing. So if I said, okay, I got one and it came out to be 120 milliwatts is what it's going to use, on this guy. That's awfully close to 125. So I certainly wouldn't use a 125 milliwatt resistor. I'd use a 250 milliwatt resistor because this is just too close. Again, it's one of those, you have to have done it for years in order to actually be always right. And still you'll make mistakes. Sorry, again, you have a question? By the way, that was a good question. Anybody else have any questions about this before we move ahead? Okay, then let me clear my whiteboard here if I can remember which keys to press. Ooh, I found it. I don't always get that one right. Device tonight. It's a transistor. And specifically, we're going to be talking about something called a bipolar transistor. Now that is not some kid that's got some, happiness days and bad days. The bipolar here means something differently. But it is a specific type of transistor that we're going to be using. Now this is opposed to a different type. Let me see, where am I typing on this now? Put it over here. What are called metal oxide semiconductor field effect transistors. That's kind of the competition for what we're dealing with. But we're not going to be talking about them directly at this point. We might later in the semester, but not for now. We're going to be talking about bipolar transistors. Bipolar transistors designed are what we're going to call current amplifiers, as opposed to a MOSFET, which is a voltage amplifier. These are made primarily, as diodes are made, out of silicon. And they basically are three-layer devices. Three layers have names. Let me put them over here. There's something called the collector, something called the base, something called the emitter. Now, these are not made out of, well, they're actually made out of pure silicon, but the silicon has been what we call doped. From a chemical element that sits in the periodic table very close to silicon. And different designs use different materials, so we won't talk about that. And we're also not going to talk about the physics of the transistors. It's not important in this class. It would be in some other classes, just not going to be in ours. We don't need to know that. We're going to think of the practical way of using them as opposed to understanding all of the physics. By all means, if you're a physics person, read about them, learn about them, but I'm not going to answer any questions about them in class. It's just too much material for this level course. So what happens is when we dope the silicon, we can create two types of material. One we call P material, which is material that has too many pluses in it. Basically, think of it as we've gotten rid of some of the electrons that are in the chemical bonding of the thing. We have N material, which has too many electrons. So if I had this perfectly formed atom, here it is, and I'm just going to stick some electrons floating around. The numbers won't be useful or correct. This has a lot of trouble combining with something else if the shell that these electrons are in is full. You have to do some things like heat and things like that in order to get it to combine with something else. However, if I add an extra electron, and it's capable of taking an extra electron, then another one like this is going to be less fond of this because their charges are too much the same, and like the same end of a magnet, they'll kind of repel each other. But let's say I had some other material, which instead of having the extra electron, I had blown one of these away so it wasn't even there and kind of left a hole. Well, the other guy that has an electron, an extra, might want to hook up with that hole and combine these two together. And if we did that repeatedly, we could actually envision an electron moving along through the structure, going from where a hole is, jumping from where no hole is to a place where a hole is, and so forth, making it look like the electrons are actually moving in a line. Of course, they're probably staying relatively close to where they live, but practically speaking of them, we could think of them as kind of coming out of the transistor. So what I'm going to do is I'm going to take 3 pieces of doped silicon, and for our purposes, although we could do it a different way, we're going to take what we call N material and sandwich some P. We're going to take some material that has too many electrons on both ends, wrap it around some material that has too many places for electrons, meaning they're open holes, and we're going to, in certain combinations, combine them to create the device we call a transistor. We draw it. I just draw a circle, draw a little flat side here, a line going up, a line coming down, put an arrowhead for now on the bottom one. And then we can connect this to the outside. So it's a 3-lead device. The center lead is the base. The top lead is the collector. And the bottom lead, emitter. Now, what I just told you about P and N material is exactly the same thing that happens with diodes when we build diodes. We make one piece of P material be sandwiched against a piece of N material, and that causes new electrons arriving from being able to pass if there's some holes for them to go into, or be rejected if the material looks too much like it's too negative. So the direction a diode goes. Same thing with a transistor. If we look between the base and the emitter, we effectively have a diode. We have something that's too positive and something that's too negative. Current can pass that direction. It can go that way. The same thing with the base collector here. We have something that's too positive and something that's too negative, perhaps, depending on what we hook it up. But the material is more negative, so left alone, current could pass out of the transistor. Now, I take a very simple look at it. What we could envision is that if the transistor were a source of electrons, they would go out the collector, they were emitted, and go out the collector and go around a circuit and come back in again. They could be blocked by putting a voltage on the base, which would basically block them from passing this point right here. In fact, that's not really the way it works, because we're not really blocking it with a voltage. We're blocking what's going on by taking these diodes and biasing them so that they are either forward or reverse biased. Now, we're going to talk about the flow of conventional current. In a transistor, a small amount of current from the base to emitter, which we will call IB, will cause a large amount of current to flow through the transistor from the collector to the emitter, electron flow. And we call that IC until it comes out of the transistor. Then it's really IB plus IC, and we call that IE, or the emitter current. So a little bit of current in causes a large amount of current to flow. They get combined and come out of the transistor as the combination. 3 names there, IB, IC, and IE. B is base, C is collector, E is the emitter. Now, we have this particular diode junction here, base to emitter. If the base is higher than the emitter, because we know this is a diode, which means it has to be at least 0.7 volts higher. So we'll just make that assumption. It's higher by 0.7 volts, then we do get current, IC flows. If, however, it's less than 0.7, or the emitter is higher than the base, no current will flow. Now we have one other set of cases up here, which are if the base and the emitter are properly biased, meaning the base is higher than the emitter, But the base and the collector have two choices. One, they can be forward biased, meaning the base is higher than the collector. Second, they could be the base is lower than the collector. These two cases both have current flowing, but the top one is called saturation. Let me actually type that. When we're working with the transistor as a switch, which is what we're probably going to want to do most of the time when we're making digital electronics, want to have the transistor be saturated. If, however, we were designing radios or amplifiers or guitar fuzz boxes or something, we would make the base collector be reverse biased, and then we'd be operating in what's called the active region. The same thing's true down here when we have the emitter and the base reverse bias, but since no current's flowing, we don't really have to worry about the base collector thing. We just assume that everything over here is in a state that we're going to call cutoff. Make that one word just for fun. So let's draw a transistor and put some numbers on it. I opened up a circuit. And I measured the voltage right here and right here. And relative to the 0 volts I saw here, I saw 0.7 volts here. Then I came over here and I measured between the base and the collector. And what I measured here, between this and this, is I came back to basically the fact that this is 0 volts. So the base is higher than the collector, and the base is higher than the emitter. Higher and higher, we would know the transistor is operating in saturation. Okay, let's assume that when I measured this spot relative to this spot, remember we're measuring relative to this 0. This is 0.7 relative to this 0. This guy is 1.2 volts relative to 0. Well, base emitter is positive. Base collector is now negative. The transistor is operating in the active region, meaning it's operating amplifier. Now, when it's operating like an amplifier, the current flowing into the base controls the amount of current flowing into the collector. And it does using the following formula. IB times beta, we can put a little DC down here. We don't always have to do that. We'll know it's there. Times beta equals IC. Beta is a characteristic that can be measured by putting the transistor into the active region and just figuring out what it is, looking at the packaging to see what it was supposed to be. From me as part of an assignment, make the assumption that beta is equal to the number 100. It's a unitless constant. So for this transistor, if we don't tell you otherwise, beta is 100. So if I told you IB equals 10 microamps and ask you what IC would be if the transistor is in active region, you would simply take 10 microamps multiply it times 100. You look at that number and say that this amplifier is amplified a signal of 10 microamps. We'll amplify it to be 1 milliamp. Now, if we're in saturation, you can't tell because it's not the transistor that's preventing extra current from flowing. It's a resistor in the circuit somewhere that's limiting it, forcing it to be in saturation. And we'll talk about that when we do a little design with this. Now, you might say, well, what the heck would we ever need to use a transistor in order to turn on an LED? Well, here's why we might. Remember our circuit we've been working with so far? It has a battery, a resistor, an LED, there's a couple of lightning bolts. It goes back to the battery. And we said this could be as high as 25 milliamps. Now we're going to replace this little piece of wire right here. We'll erase it. And we'll put a switch in. Just like a piece of wire. Right now, no current can flow, right? So the light is off. Push the switch down, the light can turn on. Now, what if I replaced what's here instead with the pin on a microcontroller, where it can either be on or it can be off? Well, if it's on, it has to be able to supply 25 microamps. What if the data sheet says the most it can do is 10 milliamps? Well, we're out of luck. We can't turn the light on with our microcontroller. However, if our transistor was able to take in some very small amount from the pin and bump it 100 times so that the value on this side was 25 milliamps, we'd be golden. We could use the transistor in conjunction with the microcontroller pin to be able to turn on something that needs too much current if you were just trying to drive it directly. Give me a green circle if that kind of makes a little bit of sense. And it could be a little tiny bit of sense. So if I wanted to have 25 milliamps over here, how much current would I have to supply? Anybody want to take a shot at the number? Robert?
250 microamps.
Well, let's see. That sounds pretty good. We know that we want to supply 0.025. The beta of the transistor is 100, right? So that means when we multiplied to get here, so we'll divide by 100 to get back to the number that would have caused that. And as you said, it's 250 microamps. If this guy is capable of producing 10 milliamps, he certainly can produce 25 or 250 microamps. So that's justification for a transistor. So any questions about what I've told you so far? Okay. Well, let us put a circuit together here. We're going to center ourselves around a transistor. And we're going to control the transistor with a battery. We'll assume we could put a switch in if we needed. We'll just draw the resistor and a resistor. And then that current that's flowing over here will come out the emitter and head back to the battery. So current on this side is called IB. This resistor is called RB. This battery is called VBB. The transistor is called Q1. The T had already been used for, that's why we don't use it. Now, this is the controlling side. So what are we going to control? Well, on the other side, we're going to put a resistor. We're going to put an LED. Now, notice this will look like it's upside down, but that's because we're really putting it in the circuit to flow that direction. This is going to be called RC. This is going to be called LED1. Current's going to flow this direction. We call that current IC. And where IC and IB come out of this, we actually have a current called IE, which we won't always show. IB plus IC. Now, Kirchhoff's voltage law says that in the closed loop, all the voltages are going to add up to 0. In here, all the voltages are going to add up to 0. So we need to make some assumptions about some things to begin our design. First of all, a reasonable thing to ask a question of is what's powering this side? And you go, oh, there's nothing. So what we need to do is we need to physically add a second battery. Now, we could share the battery, but we're going to, in our design, pretend like they have different values sometimes. The name of this battery is VCC. The C stands for it's on the collector side. The B over here stood for it's on the base side. So we're going to assume for a moment we have 5 volts on the base. And we have 9 volts on the collector side. We're measuring relative to the bottom of the batteries, which is the same spot as here, which is where ground is located. Now, because we're turning the LED on, we want the transistor to be able to provide as much current as possible, meaning we want the transistor in our design to become saturated. That's an important step. We don't want it in the active region because if it is in the active region and this varies slightly, then the light will dim and get brighter. And the saturated will pick a current, make this stay at that current, or within 5%, 10%, whatever we decide our resistor value should be. Values for our problem, and we'll see how to work this problem. Now, do you remember earlier I said that one of the desirables is that when this transistor is turned on, there's going to be a 0.7 volt drop between here and here. So that means that the voltage drop between there and 0 is 0.7 volts. So how much voltage is there right at this point? Well, it went from 0 up to 0.7 over to 5 volts. So how much voltage is dropping across that resistor? New hands, please. Mikhail?
0.7 volts.
Well, there's 0.7 right here. We're at 5 volts there. We want to know to get to 5 volts down to 0.7, how many volts is that?
3.3. No, I mean 4.3.
4.3 volts. So 4.3 plus 0.7 is going to give us the 5 volts. Now, we need to know a voltage drop across the LED. I didn't give you one, but what is it? Basu?
2.1.
2.1.
Yeah, 2.1 volts. Which means what's the voltage right at this spot right here? Raise your hand if you know. Yan Wen?
So 9 volt minus 2.1 volt is
Which
6.9 volt.
Okay, so we'd be at 6.9 volts right here. Now to get back to 0 volts, which is here, we have to drop across the resistor and a drop across the front of the transistor between the collector and the emitter. Now, in order for, we said we wanted for the transistor to be saturated, that means the base is sitting at 0.7 relative to ground. That means this guy here has to be at a value 0.7 or less. If I don't give you a value, assume that the drop across the transistor is 0 volts. That's less than 0.7, and it would mean the transistor is beyond fully saturated. So that means that if nothing drops here, the entire 6.9 has to drop across that resistor. Okay, it would be nice to know what this current is. What current do we want to have flowing in order? Put your hand up if you know, and I'll call on you. Andrew?
20 milliamps.
Yeah, 20 milliamps here. So if we have 20 milliamps flowing here, the light will be on. We'll be in saturation because this number will be less than 0.7. There'll be a 2.1 volt drop across the LED. The LED will be on. So everything will be working if we can cause this to have 0 volts across it, and also the 0.7. Now to get the 0.7, we need a moderate amount of current. The more important thing is that we're going to get enough current to saturate the transistor. Now let's think for a second. If this number right here times beta equaled this number, we would be operating as an amplifier. That was the definition. If this current times beta gives you the current over here, you're an amplifier. If, however, this current is big enough that when it's multiplied times beta, it's bigger than this number, you have to be saturated because you're not controlling it as much as the resistor is limiting it. So we need to make a base current, which when multiplied times beta, gives us a value that's bigger than this. So we're going to use a rule of thumb for that. First of all, we need a value for beta. So beta is equal to what? I didn't give you one, so what value are we going to use, Robert?
100.
Okay. Trick we're going to do. Take the current we want. Let me clear this, which is 0.020. Divide it by beta. and double your answer. So 400 microamps. So what we want to have now is this base current be 400 microamps. Because if we multiply that times beta, we're going to get 40 milliamps, which is bigger than this. That allows for imprecise selection of our resistors and everything. We could narrow it down to a smaller number. We could make it a bigger number. But for our purposes, that's the algorithm. Take the current you want in the collector, if you want to guarantee saturation, divide it by beta. Now at this point, we're pretty much done. We could go build this circuit, except we don't know the values of the resistors. Everything else we know. I think we've got all the numbers now that we're going to need to have. Let's figure out what this resistor has to be. So RC is equal to the voltage drop, which we would call VRC, across it, divided by the current through it. So VRC is 6.9, I believe, volts. The current in amps is 0.020 amps. When I do that division, I can put this where I can type on it. 6.9 divided by 0.020 is going to give me a 345 ohm resistor. Okay, we know there is no such thing. So we take the 345, take two significant digits, and it comes a 350 ohm resistor. We look at our standard chart. 360 is about the best we're going to do at 5%. So that means we're going to have a 360 ohm resistor, 5%. So we add 18 to that, would be 378. Take 18 from that. I can't do that in my head. Be as low as 342. Then we do our same exercise. We calculate the current and the wattage. We make sure that this current is not too big. We make sure that current's not too small. So this guy has to be able to, you get to 25, or I should say it's less than 25 milliamps. This guy has to be bigger than 15 milliamps. This guy has to be the wattage we're going to actually size our resistor based on. And then we're going to be able to go to the store and buy. We could get the color code for that. We've done that already. So now we'll have identified this particular resistor. Now we need to come over here and do the same for this resistor. We know that the voltage drop across it is 4.3 volts. We know that the current through it is 400 microamps. So that's 0.0004. Let's just do that. So we need a 10 or 11K ohm resistor. Of course, there won't be one. Well, there's actually in a 5%, there is an 11. So we can use the 5% 11 just as it is. We need to come down here and build the same table. You know, this is the 11 minus. This is the 11K itself. This is the 11 plus the 5%. And we do our two calculations there, a single calculation there. If everything falls into spec, we'll have the wattage, we'll have the color codes. We can go by our resistors. If we go by the resistors, and I give you an LED, which is really 2.1 and uses those specs, a transistor that really has a beta of 100, and we have 5 volt, 9 volt power supply. If we built this, this would work. It's not maybe it'll work. It's not, oh, this is too complicated, we need to do more calculations. No, if you followed my procedure I just gave you and you hook this up, this transistor will work in a saturated form. If we put a switch in here, we can turn this light on and off, even though we could assume that this piece here was a pin on the microcontroller that couldn't provide 25 or 20 milliamps of current. Why that's useful? And transistors are the basis for building digital circuitry. Give a green circle right now if you're impressed with yourself for knowing how to design a circuit. I've come on engineers that couldn't do it as quickly as we can do one. And ours works. Theirs don't always work. They get too worried about the wrong things. But it's okay to do. I mean, because once they've eventually learned it, they will build one that's much more stable than ours. But for practical and understanding what's going on under the hood, we've got this thing down pretty cold right now. So you want to make sure you have this picture and can reproduce it. You might, what today is Wednesday, I'm thinking. So that means we meet again on Monday night. You should have done one of these problems and practiced some of your other things before then. We're going to start digital logic and in a little bit. What you might try doing with one of these is, let's say you would do the same circuit, but let's change something. I'm not going to work this, so I'll never check to see that you did it, but it might be a good thing for you just to practice with. Make VBB be equal to 6 volts. Make VCC equal to 5 volts. Make the beta of the transistor be equal to 200. Make VCE, which is the drop across here where we said assume 0 if I tell you otherwise, just assume it is a 0.1 volt drop. Make the LED the LED's current values be between 10 milliamps up to 20 milliamps instead of the one we've been doing. And I think that was all the assumed values, and I think I've changed them all now for you. And then work out the problem and see if you can figure out what the resistors are. And then what I would suggest you do is talk to other people in the class, help them out if they don't know what they're doing, but also compare answers. See if you can figure out why you got what you got. See if you can follow Bostain's algorithm to the letter and be that guy who impresses everybody on Monday night by knowing how. But talk to other people in the class. Make friends. I mean, this is not a heads down class. The only thing you can't share is answers or code, you know, on a test or in a programming assignment. But when we're working on a problem like that, that'd be ideal to talk to somebody else about what everything means. You might know this perfectly, but have one concept that somebody else in the class knows, and you might be confused by it. So make friends. Pass your emails around, your phone number, whatever it is that lets you talk to other people in the class. Don't be shy. You know, try to get some friends in the class. You see who the people shooting their hands are up. Get one of them on your team. Of course, some of them shoot their hands up and give me wrong answers, but at least they're volunteering to try, which I really like. Those of you that aren't trying, I'm worried about you. For more than just you have trouble in the class, you should be taking this, learning it, and trying to move ahead. Okay, any questions before we're done for the evening? Frank?
Yeah, I'm just wondering. I'm probably thinking ahead right now. You mentioned we're going to be now basically doing a light switch, turning it on and off. Are we going to be learning how to utilize programming in order to turn that on and off switch?
You will later, but the switch itself will be a pin on a microcontroller, and it won't really be an on-off switch. But yes, absolutely, by the time we're getting to our microcontroller, we'll be able to turn an LED on and turn it off, as well as other things. It's just in this class, we don't happen to have those things to be able to build a circuit. If we were meeting together, we literally would grab all those parts out of a box, hook them up, and everybody'd be going, wow, I just got that to work. Because you just simply build the circuit we designed. This is real. I mean, we're not doing just textbook stuff. This actually works. Okay, instead of good night tonight when you leave me, you can tell me happy birthday. Today's my birthday. I have a piece of cake when this is all over. I think the cat has eaten the other piece already. So Ms. Lucy has already celebrated. But that can be your parting message to me tonight, unless, of course, you don't wish me a happy one, in which case, oh well. So good night to you folks, and I will see you on Monday at 6.
Happy birthday, Professor.
Happy birthday.
Happy birthday.
Happy birthday.
Happy birthday, Professor. Good night.
Good night.
Happy birthday, Professor. See you in the
Yep,
morning.
bye-bye. Okay, oh yeah, we have the other class together. I'll see you then.